Imagine a world where everyone spoke the same language. No more worrying about learning new languages or dealing with translation apps. Sounds great, right? Well, that's exactly what happened in the world of computer networks. Instead of each network speaking a different language, engineers got together and created a common language that all computers could understand. In this video, we'll find out how this common language came to be, and I'll show you what's happening behind the scenes in a fun and simple way. Let's jump right in. In our last video, we learned about packet switching. Robert and his team faced a big challenge, sending lots of data smoothly over the network. Their solution was clever. They broke down large pieces of data into smaller parts called packets. Each packet got its own destination address, telling it exactly where to go. But how could these packets know their correct order? That's where the sequence number comes in. Think of it like numbering pages in a book. Even if pages get mixed up, you can easily put them back into the correct order. The entire system of breaking data into packets, labeling them, and sending them off is what we call a networking model. It's simply a set of rules that help computers communicate clearly and efficiently. Robert's team didn't stop there. They applied these rules to all their computers. Now, every device in the network could communicate smoothly, without confusion. Now that we know what a networking model is, let's see how different companies created their own, and why this led to tricky challenges. In the early days of networking, each company had its own way of making computers communicate. IBM, DEC, and other big companies created their own ways for computers to talk to each other. Imagine every country speaking a completely different language without translation. It would be really hard to communicate, right? Well, that's exactly what happened with early computer networks. Initially, this wasn't a big issue, but soon it became a serious problem. Computers from different companies struggled to communicate clearly because they followed different rules. Network engineers always had to deal with different networking models and set up separate networks just to keep things running. The big question was, could these networks even connect? Or did businesses have to commit to just one brand forever? To solve this confusion, two major networking models were created, the OSI model and the TCP/IP model. But why did we end up with two different models? And what role do they play today? To solve communication issues between different networks, the International Organization for Standardization, ISO, created the OSI model. They divided all networking rules into 7 clear layers. Each layer had its own specific job in network communication. The goal was simple: create a clear structure that everyone could easily understand. The OSI model became very popular because it clearly explained how networks worked. It was such a big success that it even won a Nobel Prize. At the same time, another group was working on the same problem, but in a more practical way. The U.S. Department of Defense, DoD, joined researchers from top American universities. Together, they created a simpler, practical model called TCP/IP. Unlike the OSI model, TCP/IP was built specifically for real-world use. It quickly became popular, especially in universities and research labs. Today, TCP/IP is the foundation of the modern internet. It connects billions of devices and networks all over the world. Now, how exactly did TCP/IP become so important? Let's find out next. Back in the early 1990s, many companies used both TCP/IP and OSI models. This helped engineers connect different types of devices and easily manage networks. But soon, networks became very complicated. By the late 90s and early 2000s, using both OSI and TCP/IP became expensive, confusing, and created major compatibility issues. To simplify things and save money, companies began phasing out OSI and focused completely on TCP/IP. That's how TCP/IP became the world's main networking standard. Almost every company, university, and organization switched entirely to TCP/IP. Meanwhile, the OSI model gradually disappeared from everyday use. Today, it's mostly mentioned in textbooks and classrooms. But why did this happen? Why do you think TCP/IP became more popular than the OSI model? Let me know your ideas in the comments. But wait, what exactly is TCP/IP? And how does it really work behind the scenes? Let's dive in next and take a closer look. Ever wondered what really happens behind the scenes when you browse the internet? How does a simple click bring websites, videos, and messages right to your screen in seconds? Behind every web page and every message you send, there's an organized system, a set of rules that computers around the world follow. These rules are called protocols, and they're grouped into clear layers, known as the TCP/IP model. To make things simple, imagine the TCP/IP model as a library with 4 shelves. Each shelf represents a different layer of TCP/IP, and the books on each shelf? Those are the rules and guidelines called protocols that help data move smoothly between computers and networks. Just like books in a library, these protocols are carefully grouped by their roles, making it easy for everyone to understand how the internet works. Let's quickly explore each shelf. First shelf, the network access layer. This shelf is all about getting data moving. It covers everything physical, like cables, Wi-Fi signals, and hardware such as NICs, routers, and switches. Think of this shelf as the foundation of TCP/IP. Without it, data simply can't travel, but it doesn't stop there. This shelf also explains how data moves from your device to the first stop, like your Wi-Fi router or a nearby switch. It's like handing your letter to the local post office, the very first step in sending your message over the network. Second shelf, the network layer. This shelf is all about finding the best path for data to reach its destination. Imagine the Postal Service carefully deciding how to deliver your letter from your city to another city, figuring out the quickest or safest route along the way. This is exactly what's happening in the network layer. Here, important rules and guidelines, such as IP addresses and packet forwarding, come into action. Routers act like traffic controllers, choosing the most efficient paths for your data packets, making sure everything reaches the right destination smoothly. Network engineers spend a lot of time working at this layer, ensuring data travels quickly and reliably through the network. Third shelf, the transport layer. This layer makes sure your data not only arrives at its destination, but also arrives correctly and in the exact right order. Imagine sending a letter, but along the way, one of the pages gets lost or damaged. Without this page, your message wouldn't make sense. That's exactly what the transport layer fixes. It carefully checks that every piece of your message arrives intact. If something goes missing or gets damaged, protocols like TCP step in. They request the missing or corrupted data to be sent again. This ensures the entire message makes perfect sense once it arrives. Fourth shelf, the application layer. This shelf includes all the protocols that your everyday apps rely on, like your web browser, email services, and messaging apps. It's like the front desk of a library, helping you request exactly what you need. Protocols here define how applications request information, how servers respond, and how data is formatted and presented. Software developers rely on these guidelines to make sure all your apps communicate smoothly and quickly over the network, providing you a seamless internet experience every day. All right, in this video, we got familiar with networking models. We explored TCP/IP and the OSI model, and we saw how TCP/IP became the standard. Then we broke down the TCP/IP protocol and got a quick overview of what happens at each layer. But this is just the beginning. In the next video, we'll take a closer look at each layer and explore the most important protocols that keep the internet running. So, stay tuned. And if you haven't already, make sure to like, subscribe, and hit that notification bell so you don't miss out. Thanks for watching, and I'll see you in the next one.